Okay, so we only got just a few slides left in chapter 5, and then we're going to move on to chapter 10 today, which is the CVC chapter, complete blood count. We'll talk about it, and then we'll come back and pick up hemoglobin. Okay, study guides, I put them online, right? They're already online. The paper one and the computer one are the same, right? They're not the same? Have y'all looked at the paper one that I always put one that's a paper one, and then the one that, have you done the computer one?
I have. I think there's some different.
I have. There are different questions.
There are different questions?
I believe so.
Yeah.
Well, that's not good. Y'all got to tell me that. So I need to fix that. I need to take the paper one off and make it the same as the computer one. Okay? And I was afraid of that because I had a couple of them in my files and I didn't know exactly which ones.
Yeah, it was just a few.
Well, I know, but that few can make a difference.
Yeah.
You know?
I thought
So,
that was crazy.
no, I mean, I was going to ask you guys to make sure that, there wasn't messed up. Okay, so I'll look at it and I'll make sure I get the right two on there. I'm going to leave the computer one. The computer one's the one your test's going to be. Okay? The one that's on the computer will be the actual test. Okay? But I'll look at the paper one and see if I can figure out. What, girl? Dang.
Well, I want to know, like, where we're skipping. Are we skipping ahead or am I just...
Yeah, because
We didn't skip much ahead. We skipped a little bit ahead, but I mean, not anything that we didn't talk about. Talking about RBC destruction.
That is right before that. The regulation of erythrocyte.
Yeah, we talked about that. Yeah, talked about EPO and all that kind of stuff. Yeah. All right, so let's talk about erythrocyte destruction. So there are two types of destruction that can occur, and we're going to talk about these two types. Most RBC destruction normally is...
that?
What page is this? Hang on, and I will tell you exactly what page.
Or what slide is it?
Oh, no, slide it is slide 194 is what I have.
Okay.
Is that right?
Yeah.
Yes.
Okay.
Yes. Okay.
All right. Page-wise, in the chapter, it is page... Second.
And then where are we going?
Chapter 10.
Because like they're not all labeled.
Page 72. So it's very little bit left in the chapter. Huh?
The next one we're going to, where's chapter 10? What slide does it start on?
I don't know, like 100 and something, 200 and something.
I thought we stopped on the kinetics. And I'm just...
We talked about kinetics.
Right.
I just mentioned it because I mentioned kinetics is basically just like ranges. We talked about sex and, males and females. We've mentioned that a bunch of times in here in this class already. So I said I'm not going to spend time on that. You guys can just look over that. And then we talked about regulation of the erythrocyte production. We talked about how that, EPO is what regulates it, but things like altitude, those kind of things change it. We've talked about that several times in the class, so that's what that was all about. So the thing that we want to get to today, so we can finish up the red cell stuff, is the destruction. Okay. All right. Everybody with me? Okay. All right. So erythrocyte destruction. So RBC destruction is normally the result of senescence. Senescence, everybody, you want to say it? Senescence, I guess is how it's actually pronounced. That simply means old age. It just means the cell's not efficient anymore, and it's reached an age where it's not being efficient, doing what it's supposed to do. So, what characterizes aging? A couple of different things. One of the big things is the decline in the cellular enzyme system. That, remember we talked about, it still has to do respiration. That cell's doing respiration, it's doing anaerobic respiration, but all respiration requires enzymes. So we talked about the Embden-Meyer-Hoffman. We talked a little bit about the hexo monophosphate shunt. I mentioned G6PD deficiency and all that stuff and told you to kind of look over that. So that's what it's talking about. Anytime those glycolytic enzymes decrease, then you know you can't produce the ATP that the cell needs to survive. And so now it's not being as efficient as it should be. So these are things that are going to lead to destruction of the cell, okay? All right? Anytime you have that loss of ATP production and the loss of reducing systems, then you begin to have oxidations that are occurring that become detrimental to the cell itself, okay? So those cells are unable to maintain their cell shape, their deformability, all these different things. And so now we need to get rid of them. And so we know that most of this is going to occur where? In the spleen, right? So the spleen is where this is occurring. We want about 90% of our red cell destruction to occur in the spleen, okay? It is known as extravascular destruction, okay? Extravascular destruction is removed by the spleen, bone marrow, or the liver, okay? So essentially where extramedullary hematopoiesis occurs, remember, okay, spleen and liver and the thymus, okay? Part of the spleen and the liver are also part of extravascular hemolysis or destruction, okay? Extravascular hemolysis is also a term that can be used because we're going to hemolyze those red blood cells, okay? We call it extravascular destruction, but hemolysis would be okay to use because that's what's going to happen, all right? 90% of the aged RBC destruction occurs here. It is the most efficient method of cell removal, okay? Conserving and recycling amino acids and iron, okay? And this is where they need to occur, all right? Any questions about that? All right? Remember, we have those macrophages in the spleen that basically do this. In the spleen where this is taking place, it is a very hypoxic. What does hypoxic mean? Low oxygen. Hypoglycemic environment. So what's hypoglycemic mean?
Low sugar.
Low sugar, right? Hypo always means low, okay? So hypoxic is a low in oxygen environment and also low glucose environment where these cells are going to be destroyed, okay? This occurs in the macrophages of the liver. The liver lacks the ability to detect minimal defects, though, okay? So a lot of times when it's happening in the liver, it's just destroying them. Whereas in the spleen, sometimes instead of destroying the whole cell, it'll try to get rid of whatever's the problem. Like we talked about those Heinz bodies, when the hemoglobin gets oxidized and becomes granules, okay, precipitates, then it reaches out, those macrophages reach out and try to bite the cell. So you get helmet cells or bite cells, okay? The spleen has a larger ability to be more choosy about what it destroys, whereas the liver doesn't. The liver, if it senses that there's something wrong with the cell, it just destroys it. It doesn't try to help it get any better. So, more efficient than the spleen in removing RBCs due to more RBC circulation throughput. So what that means is, yes, the liver is more efficient, but it's not as picky as the spleen is. And plus, there's more blood going through the liver than the spleen. That's one of the reasons why it's more efficient. The spleen is actually more efficient because it is a little more choosy. Those macrophages have a little more discretion on which cells to pull than the liver cells do, okay? All right, questions about that, guys? Okay, so extravascular destruction, the two main places that we want it to occur is the spleen and the liver, and we know that it does occur in the bone marrow also. Those macrophages in the bone marrow can do that also, okay? The one we don't want to occur, and we only want about 10% or less to occur, is intravascular, okay? Intravascular means just like what it sounds, inside the vessels, okay? So inside the arteries and veins, we don't want this to occur that often. And if we do, it should occur in very small amounts, all right? If it tends to occur more, you have an increase in what we call intravascular destruction, we have a problem, okay? All right. One of the biggest things that we worry about in the lab is transfusion reactions. Okay, so like I gave you the wrong blood type, or I gave you blood and your patient had an antibody to the blood. Okay, and so their body is starting to bust or lyse those red blood cells. Okay, so that occurs inside. We have a big chain reaction that begins to occur. And it basically just kind of damages the body system a little bit, okay? You start having too much intravascular destruction, then of course it leads to death, okay? Results in cell lysis and release of hemoglobin directly into circulation. Luckily we have special proteins. One of them is called haptoglobin. The other one is called hemopexin. These two proteins are available to bind with hemoglobin, free hemoglobin, and carry it to the liver to be destroyed or broken down. Yes?
What was the second word?
Hemopexin. Okay? And we'll talk more about those in the next chapter when we talk about hemoglobin. Okay? But right now, they are some proteins to help us carry it away. Okay? So 10% of your RBC destruction does occur intravascular. We just don't want it to be more than that 10%. Okay? And there's the words right there. Plasma proteins, haptoglobin and hemopexin. They bind to the free hemoglobin, then carry it to the liver to be catabolized. Okay? Catabolized means to be broken down, if you guys don't know that term. Okay? And we will learn heme breakdown in the hemoglobin chapter. Okay, heme is broken down in a very specific way, and the byproducts of that we use to help determine if there's intravascular hemolysis occurring. Okay, and we'll talk about that in the next chapter, or in chapter 6 when we talk about hemoglobin after chapter 10 today. Okay. Questions about intravascular destruction or extravascular destruction? All right, so let's move along to the next section here. All right, so we're going to skip hemoglobin stuff, and we're going to go to slide 190 is where we're going to start, if that'll help you guys. Slide 190. It says introduction, 3 phases of the complete blood count. Okay. CBC. All right. So every class that we have taught you guys in, I'm sure Ms. Cole's done the same thing. I know I have. 131. We talked about pre-analytical, analytical, post-analytical. Okay. They're trying to use those 3 words instead of pre-examination, examination, post-examination. It's the same thing, okay? Those words are always the same. So, 3 phases of the complete blood count that we're going to talk about. We're going to talk about pre-examination. This is patient ID, drawing the blood in the right tube, getting it to the lab in an acceptable manner, and those kind of things, okay? We've talked about that several times in 131. Now we're mentioning it in hematology. Okay? All right? During the examination process, this is what we're going to talk about the majority of this chapter. Okay? It's talking about the actual examination process. So what does that include? That includes putting the blood on an analyzer and basically getting a concentration of the WBCs, RBCs, and the platelets. So in other words, their counts. WBC counts, RBC counts, platelet counts. Okay? Categorizing the WBCs. In other words, doing a differential on them. Okay? Those are things that are done in the examination phase. And then we mentioned indices one time before early in the semester, but today in this chapter we're going to talk about what RBC indices there are. What did I say about indices? Y'all remember? Are they analyzed or are they calculated? They're calculated. Indices. Anytime you see the word indices in anything, okay? If you ever take a statistics class later on, and if you guys go on and get your MLS, you may have to take a stats class, and that's perfectly fine. You'll do fine in it. Indices is anything that's calculated. In other words, it's not a direct measurement. It's a calculation of data that you already have, okay? So RBC indices are all calculations of things that you're going to get from a direct measurement. RBC, hemoglobin, hematocrit, okay, as we go. All right, then we have post-examination. And post-examination is not that big of a deal to us in the lab. It's more like secretarial, those kind of things. But you have to make sure that you are sending the results in the computer. So we won't spend a whole lot of time talking about reporting results, but interpreting data we do look at a little bit in here. Even though us as lab techs, we're not really supposed to diagnose patients, we still need to make sure that our results are compatible with life, you know, and interpret what's going on based off of those results, okay? All right, those are the three phases, all right? So pre-examination, CBC, we definitely want to make sure that we have the right patient that we're doing the CBC on. Specimen collection, they need to be done in EDTA tubes, okay? Purple lavender top tubes that have EDTA. A lot of the hospitals now are using K2 EDTA. They had taken ethylene, diamine, tetraacetic acid, and they've added potassium to it. And potassium basically just kind of preserves the morphology of the cells. They don't lose their shape and those kind of things in the tube. And so that's one of the things that you'll see a lot now in the lab is a K2 EDTA, okay? But the big deal is EDTA, all right? Now I'm going to muddy the water a little bit. Push comes to shove, you can always do a CBC off of a sodium citrate tube. You can do a CBC off of a light blue tube, okay? The difference is that anticoagulant to blood ratio. Remember, what did I say? That blue tops always have to have what? Why do they have to be full? Because they need to be what? You remember that from phlebotomy? Said they always have to be full because you have to maintain a what ratio? Blood to anticoagulant is a what? 9-to-1 ratio, okay? So you have a lot more anticoagulant in a sodium citrate tube than you do in EDTA, okay? So that's going to kind of dilute your sample out when you run it through the machine. So you have to do a little calculation. You have to multiply everything by a certain number to get your actual results, okay? So most hospitals don't want to do a CBC off of a blue top tube. It can be done, but they don't want to do it, all right? Now later on, I'm going to talk about a phenomenon known as platelet satellitism. And we're going to talk about it in this chapter. But platelet satellitism is actually can be fixed by drawing a sodium citrate tube, by drawing the blue top tube and then making your slides with it, okay? It's a thing that the EDTA causes platelets in some people to be attracted to the neutrophils. And so every neutrophil has a bunch of platelets surrounding it. So they call it platelet satellitism, okay, as we go. We'll talk more about it a little later on. All right, any questions about that? Okay, so specimen handling, proper transport, time and temperature. Needs to be, if you're going to make a blood smear, it needs to be made within about 3 hours of collection. And then analysis needs to take place about 6 to 8 hours, no more than 6 to 8 hours, okay? There are some hospitals that about 4 or 5 hours and they say no, they're not going to do it. So, you know, it just depends on your hospital, okay? You always go by your protocols for your analysis, okay? So, automated results, instrumentation utilizes different technologies. So one of the things about pre-examination is the reason they're putting this in here is you need to make sure your machine's working, right? The machine needs to be controlled, maintained, had maintenance done on it properly, all those kind of things to make sure that you're going to be able to turn out good examination results, okay? So even though examination is what we're concerned with, pre-exam stuff requires maintenance of your analyzer, making sure that it's working the way it's supposed to, okay? All right? So, this word, I mentioned to you guys before. WBCs, RBCs, and platelets are measured by impedance and optical light. So this is where I taught you guys the other day. We said there's essentially a tube, all right? And you've got electricity going through in a solution, an electrolyte solution, okay? There's a tube that pushes the blood through, okay? And basically those cells go through, and when they hit the electrical impulse that's going down, they impede that pulse from going from this end to this end. So every time that it impedes, there's a counter down here, and I know this sounds real simple, but it really is. It's complicated computer-wise, but it's simple that every time it gets impeded, the electric flow, it says, there's a cell, there's a cell, there's a cell, okay? And then it spits out the count based off of that impedance, okay? Now, most instruments have two different chambers, okay? They have an RBC chamber that is doing red blood cells that way. Then it has a WBC platelet, okay, and a hemoglobin chamber, all right? And it's usually round, like a cup, okay? And it shoots stuff in, the sample in, okay? But then it also has the same impedance as it goes through. So it's getting the flow or the electrical impulse going through, but it's also got a laser light that is shining on the cells as they go through, okay? So in this case, what it's doing, it's not only looking at the number of cells coming through, but based off of the light scatter, it's picking up granules in the white cells. It's picking up the size of the nucleus based off of the cytoplasm for like lymphocytes and monocytes, and then the granules for eos, basos, and neutrophils, okay? Based off of how they scatter light, all right? And of course, their size plays a big role too, okay? Then, also in here, all right? So a red cell over here, we know it contains the hemoglobin inside. So for us to measure the hemoglobin, what do we have to do to that cell? We have to lyse it. We have to bust it open, right? So what happens is, in this chamber, a lysine reagent is added, okay? It's actually known as the cyano met hemoglobin method, okay? This one is not used as much anymore because of the cyanide. Cyanide, the chemical cyanide, it's a poison, you know, but it also is will lyse red blood cells, and then it binds with hemoglobin, and then oxidizes to form met hemoglobin. Okay, this basically, when those cells lyse, they release the hemoglobin in there, and then you have a spectrophotometer. Inside the machine also, and it measures the amount of particles or the light that can go through, just like a spectrophotometer works. Remember we talked about spectrophotometer in 131, right? Light scatter. Y'all remember that? Y'all used it one day, didn't you? Didn't y'all use the spectrophotometer when you was doing your pipetting, and we measured the difference in our light? Okay, so that spectrophotometer works the same way. It has a standard. Basically, you measure the standard, and then when you put your lysine reagent in, it makes the cells lyse, and then the spectrophotometer gives us our hemoglobin concentration. Okay, so those 4 things are actually measured. And there's another thing that we'll talk about. It's kind of crazy, but MCV is actually measured on most instruments. All right, and we'll talk about that in just a minute. Okay, and then everything else is calculated. Everything else you get on a CVC that we're going to look at is actually an indice. It's actually counted. It's not directly measured. Okay. All right. So cell populations, interfering substances, instrument function, all these things are determined by the instrument cell. All right, so scatter plots and histograms. We're not really going to talk about that right now. But histograms, y'all know what a histogram is? A histogram is just a term for a graph. It's just a different type of graph, okay? Most of the time it's like a number of cells, okay, versus size of the cells, okay? So what you're going to see is you're going to see a graph that's going to look like this, okay, on your machine. All right, and then these numbers are going to be anywhere from like 50, and this is femtoliter. That's the volume that we use, okay? Femtoliter. All right, that's, you remember nano, what I'll tell you guys, you know, we got gram, liter, meter, then we got deci, centi, milli, and we said there's 2 places, and you got micro, and then 2 more places, and you got nano. Well, femto is about right here. Okay? One of those dots is like femto. Nobody ever uses it, but in hematology. We do use it in hematology. Okay? So what we're looking for, femtoliter is actually what we use for the MCV. And we'll talk about mean corpuscular volume in just a minute, but that's what we actually use. But what we're looking for is, this is the RBC population, okay? So like 50, what we want is all of our red cells to fall within 80 to 100 femtoliters, okay? This is where your majority of your spikes should be. Does that make sense? Because that's what size a red cell really should be. It should have between 80 to 100 femtoliters in volume of the cell, okay? So what would happen is, let's say that I've got a chart that looks something like this, okay? And everything's over here on this side. Well, what that tells me is, let's say that's 110, 115, 120, and so forth. What that means is, when I look at a slide, is I ought to see macrocytes. Macrocytes, which are large red blood cells. Okay? So in other words, they're not normal. They're large. Okay? And then I may see something like this. Okay? I may see a population like this in my red cells. And if I do this, that means they're between 50 and 80, so they're microcytes. Okay? Alright, so that's how histograms work. And we actually have histograms for platelets, RBCs, and WBCs. Okay? Does that make sense? Alright? If you want to see these, what I'm talking about, you got your textbook? Y'all got your textbook with you? Let me see your textbook. Way in the back of your book, chapter 39, I think, maybe. Let me look here. 37, 39, yes. page 39, or chapter 39, which is on page 831, is where it starts. Page 831. If you'll look through that, it kind of gives you what I'm talking about, histograms. You can see one on page 832. That's a typical histogram. This one is an RBC one. Okay? You'll see it right here, guys. If you don't have your book, and you get your book, look at it. Okay? It's on page 832. But you can see how it's got population or number, the amount of them, and then it's got their size on the bottom. And you can see where they spike is in between. That's where you're having the most population. So it really should always fall. The high spike should be between 80 and 100 femtoliters. Anything in front of that, you're going to have microcytes, which are small cells. And anything above that 100, you're going to have macrocytes, which are large cells. And those two things are abnormal. You really shouldn't have them. They should always look the same as these. Okay? All right. So hold that out just a minute. I'm going to show histograms. All right. Now, scatter plots or histograms, that's what histograms are. Scatter plots are just like what they sound like. So in a scatter plot, it does exactly the same as a graph, okay? But all it's done is taken a bar graph and it's changed it to plots. And so what happens is you'll have like size, and then like light scatter, I believe is usually what it is. And of course that's all calculated from your machine. But what you have to learn is it puts little dots based off of cell population and their size. And like what's really cool, on your instrument, these are all color coded. Okay? They're color coded based off of your machine. Like, so what happens is you get like a little population, and then sometimes you get like trash, and it'll be always in here. So what happens is you get a population of different cells. So like this is the lymphocytes, this is your neutrophils, this is your EOs, or I'm sorry, this is probably your monos, this would be your EOs, and this would be your basos, okay? And then this is usually trash. It's usually like things that's picking up in the light scatter, okay? And so you'll see these charts, and like I said, on your instrument, they'll actually be color-coded. So like white may be lymphocytes, blue may be neutrophils, red is EOs and monos, you know, that kind of thing. So it makes it a little easier to figure out what the populations are. But these are scatter plots. So based off of the number and the intensity of the scatter plot color, that corresponds to the more cells you have, okay? So like, and then like over here, you may get a little population of immature cells. So these would be immature. Okay, so these would be like blast or myelocytes or metamyelocytes or lymphoblast or something like that. Okay, so you would always want this one to be very small. Okay, if you saw this huge area of this area, then you know you're probably dealing with some type of leukemia on the patient. Does that make sense? And it's all based off of this. We know that we should have more neutrophils than we have lymphocytes. We should have more lymphocytes than we have monocytes, and those kind of things based off of our kinetics. We know what our normal ranges should be. Okay, so if this is our neutrophil, this is where the intensity should be on a sample, is because we know that neutrophils should make up the majority of the population of white blood cells. Does that make sense to you guys? Okay. So histograms and scatter plots. These are all going to come from your machine. All right. So here are normal ranges for you guys. You need to be familiar with these normal ranges. This is what you're going to see on most instruments. Okay. This is going to be what you see on most instruments. All right. So notice that it's times 10 to the third per microliter. This also may be millimeters cubed. Okay. Somewhere in your brain, jot down millimeter cubed. Because a 1 microliter and a millimeter cubed are the same. It's the same measurement. Okay? Alright. So, 4.5 to 11,000 is what the 3 means per microliter or millimeter cubed. 4 to 5.5 million, 6 is a million per microliter. Hemoglobin 12 to 17. Of course, this is including male and female. It's a little bit different ranges, these two, for male and female. Hematocrit 36 to 52%. Okay, it is percent because that's the percent of the population or the cells, the blood volume. 80 to 100, the mean cell volume, which is MCV, is femtoliter. What that stands for, 80 to 100. MCH, we don't really look at MCH that much, but you do need to be familiar with it. This is basically the volume or the weight of hemoglobin inside a cell. Okay, mean cell hemoglobin, so basically the average cell hemoglobin. Anytime you see mean, it's not talking about like me, mean. It's talking about the average, right? Y'all understand that, correct? Okay, so average cell weight is essentially what you could say. It's 28 to 34 picograms. This is picogram. Okay, is what PG stands for. Picogram. Okay. Now MCHC we do look at. Okay, this one is important to us in the lab. We look at MCV, MCHC. Okay. Mean cell hemoglobin concentration, 32 to 36, okay? Anything below 32, we consider it hypochromic. Anything above it, we consider hyperchromic. And we'll talk about those 3 terms in just a minute, all right? Red cell distribution width. This lets us know that there's different sizes of red cells in our blood, okay? The higher the percentage, the more different sizes you have. And the term for that, we're going to talk about it in a minute, is called anisiocytosis. Anisiocytosis. Okay. I'll put it up there in just a minute. You know, I have to write it down. We'll talk about that in just a minute. Okay. Reticulocyte count, like I told you guys earlier, most instruments now do a retic, or have the capability of doing reticulocyte count. So relative and absolute. Platelet count. Mean platelet count volume is the same as RDW, except it's dealing with the platelet. Okay? RDW deals with the red cell. MPV deals with the size of the platelets, whether you have a bunch of large platelets or not. Okay? And then the diff. And we've talked about the diff already. Okay, the difference is this is the percentage, which is like what's counted. And then this is the absolute. So this is actually looking at the number of cells that are there. Okay? Most hospitals don't use the absolute count except for the neutrophil. If the absolute count ever gets below 1 on neutrophil, that's considered a critical value for the patient, because that patient is very susceptible to getting an infection if they don't have at least, what would that be, 1 billion times 9, 10 to the 9. So if they don't have at least 1 billion neutrophils, they're prone to an infection, bacterial infection. Okay? So when you're doing cancer patients, or you see these patients that have really, really low white counts, your brain will have to learn to go to this absolute and look at it and make sure that it's above 1. It needs to always be above 1. Okay? And we'll talk about that later on. And you'll learn that when you get into clinicals also. Okay? All right, questions about these parameters, normal ranges. Okay? Listen to me. It is very necessary for you guys to know these normal ranges. Okay? Or at least be familiar, close. You know what I mean? With these. All right? Because what I tell you guys, what's hematology all about? Recognizing what? Abnormal, right? Okay. If you can't recognize it, if you don't know abnormal, you're not going to recognize abnormal, correct? So you need to make sure you know what's normal, and then you'll be okay with abnormal. All right? So WBC count, erythrocyte count, hematocrit, and hemoglobin, these are usually measured results with the exception of hematocrit, and they really shouldn't put this up there because it's kind of deceiving. Some instruments might measure directly the hematocrit, but the hematocrit a lot of times calculated using the RBC and the MCV result. Okay. Even though MCV is considered an indice, a lot of your instruments now, that's how they're calculating the actual hematocrit, is they're measuring the MCV, that light, the size of the cells going through that impedance, and the light, they're able to see what size cells they are. And so by the count and the volume, they're able to basically calculate the percentage of red cells. Okay? All right. So WBC is reported as 10 to the 9th per liter or 10 to the 3rd per microliter, which is what most hospitals do this. So if you want to jot down extra right there, white cell WBC is actually 10 to the 3rd per microliter, okay? And an RBC is usually 10 to the 6th per microliter. A little bigger, better 3. That April girl be getting mad at me. She ain't here no more though, is she? Okay. All right. Hematocrit is always in the lab, is usually reported as percent. It can be reported as liter per liter. So it's going to be usually a really small decimal number. But percentage is usually what we use. Okay. What does hematocrit do? Measures the volume of the RBCs occupied within whole blood. Remember I told you guys if I put you in a centrifuge and spun you down, packed your cells to your feet, where your blood would go. Usually calculated in automation. MCV times the RBC divided by 1,000 equals the hematocrit liter per liter. So it's going to be a decimal number. You just move your decimal 2 places to the left and add, to the right and add a percent sign is usually what you do. Okay. Hemoglobin is always or usually reported as grams per deciliter instead of grams per liter. It's usually grams per deciliter. So that's the reason you're getting that 12 to 17 for it. If you were doing grams per liter, it would actually be a little smaller number of a decimal number. Okay. All right. Okay. We talked about diurnal variation in phlebotomy. Does anybody remember what diurnal means? What? How many times? What does di mean? 2. 2 times. So basically what it's saying is 2 times of the day or 2 different times of the day you have a difference in the variation. So white cell count can be different in the morning than it is at night. Okay? And that's what it's talking about. Usually that's the one, but the RBC and hematocrit can do that too. Hemoglobin tends to not be, but it can be also. So you can have some diurnal variation in CBCs. So a lot of times you may see a CBC done in the morning and then one done at night, just to kind of compare the two because of that diurnal variation. Okay? All right, something very, very important that you guys need to learn. You need to know this. Rule of 3. Okay? Rule of 3 is very, very important because you will learn as you become a tech and become a seasoned tech especially, how to always look at your CBC reports and do the rule of 3. You will always look at your RBC count, okay, times 3 equals your hemoglobin. okay? Then your hemoglobin times 3 should equal your hematocrit, all right? I'm going to go ahead and tell you, most texts leave the RBC part out. We look at the hemoglobin times 3 equals the hematocrit. That's the one we focus on most of the time. Hemoglobin times 3 equals the hematocrit plus or minus 3. Does that make sense? So if I've got a 5 hemoglobin, which is not normal, but makes math easy for me, all right? If my hemoglobin's 5, my hematocrit better be 15 plus or minus 3. Now it can vary a little bit, okay? That's the reason we get that plus or minus 3, okay? Just based off the size of the cells and that kind of thing, all right? So that's a big rule that you guys need to know. So let me ask you something, Kim. You think it's probably going to be on your quiz come Wednesday?
Yeah.
I bet it is, okay? So rule of 3 is important, okay? And unfortunately, there's also another rule of 3 in blood bank you guys will learn later on. But don't get those two confused, okay? Rule of 3, hemoglobin times 3 equals the hematocrit plus or minus 3. That's the big part of this that I want you to know. Now, technically, the RBC times 3 should equal the hemoglobin, okay? But this one's the big one right here, plus or minus 3. Hemoglobin equals the hematocrit. And you'll learn in your head how to do things by 3 really, really quick, you know, as you do it. Questions about that, guys? All right. RBC indices. So let's talk about these for a little bit. They help classify RBCs. So what do we mean by classifying RBCs? We mean their size. There are 3 classes of RBCs that we can talk about. We call them. The one that does this is our MCV. And I'm probably getting a little bit ahead of myself, but it'll be all right. Huh?
No.
It won't be all right. All right, so MCV stands for mean corpuscular volume. Okay, so essentially the size of the cell. Or the average size of your cell. Okay? So MCV normal is 80 to 100 femtoliters. Okay? If it is 80 to 100 femtoliters, it is known as a normocyte. Normocyte. I think it's an A, maybe an O. We'll look at it in a minute. It's an O here, normocyte. Okay, sorry. Normocyte. Okay, normocyte. All right, MCV is less than 80 femtoliters. We have microcytes or microcyte. Everybody you want to say it, it's fine with me. I call it a microcyte. Okay, if you want to call it microcyte, knock yourself out. All right, this fan's got to go. Heater's got to go, guys. Burning the guy up here. Okay? I could. All right. What's the old saying? You can always put on more clothes than I can take off. All right. MCV greater than 100 femtoliters. Cells are known as macrocytes. All right. This is the 3 terms we use to describe red blood cells. Okay. Size-wise. Microcyte, normocyte, macrocytes. Okay? And it's all based off of the MCV. Alright? Now, MCV, MCH, and MCHC, we're going to talk about those individually. So that's the reason I didn't spend that much time on them. Okay? So let's talk about the MCV in general. All right, so it's the average volume of the individual cells. Okay. It says mean cell volume. I was not taught it was mean corpuscular volume, but that's the reason I put that up there. But if you want to call it mean cell volume, that's perfectly fine with me. Okay. I'm old school. Remember, I'm old. Okay. Average volume of the individual RBCs expressed in femtoliters. Okay. So I kind of lied to y'all on the little thing over here. Femtoliter would actually be like here, right?
After my,
Yeah, it would actually be after micro instead of before micro, because nano is what, 12 to the 12, well, technically negative 12, right? Is that right? Because micro's 9, so 10, 11, 12, 13, 14, 15. So femto would be, what's that be, a trillion? Be a trillionth of a liter, or a liter in this case, trillionth of a liter. Okay, so tiny, right? Okay, so femto measured directly on automated cell counters, and this is what I was talking about earlier. So most of your machines are actually measuring, even though we put it in the RBC indices, it is actually measured when that impedance is occurring. There's a light shining on it, and it's measuring the size of those cells. Okay. And then taking the average of these, okay? It can be manually calculated. You can do it manually by taking the hematocrit times 1,000 divided by your RBC counts, okay? You need to know how to calculate an MCV manually, all right? So you need to know this formula, all right? Hematocrit times 1,000 divided by your RBC count. You have to make sure that they're in liters, okay? Make sure they're both in liters. And this equals the MCV in femtoliters. Okay? Reference intervals 80 to 100. Very, very important to know this, okay? 80 to 100, important to know the range. Okay? Because if you don't know the range, you can't get the cells, right? You don't know the classification of the cells, all right? So, normocytic, microcytic, macrocytic, okay? Can also be normocyte, microcyte, macrocyte, okay? Talking about one, all right? Correlates with the appearance of the cell on the smear, all right? So we're going to talk about a thing called a morphology, all right? When you do your morphologies, you're looking at the red blood cells, okay? We also look at the platelets a little bit, but mostly the RBCs, all right? So you guys have been doing diffs on the slides downstairs. Now you're going to start doing morphologies on the slides downstairs. So one of the things you need to look at is the size of the red cells, okay? And you need to judge, all right, by 1 plus, 2 plus, 3 plus, 4 plus, okay? If they're, now listen, if they're normal, we don't comment on it. But if there's microcytes or macrocytes present, then we comment on it. Does that make sense? And I'm going to talk to you about how to do it a little later on, all right? When we start in lab tomorrow. I'm actually going to talk about it a little bit in lab, all right? So, increased MCV, so above 100, anything above 100, you're going to have macrocytes. Anything below 80, you're going to have microcytes or microcytes, okay? Questions about that, guys? All right. Abnormalities provide clues to the disease process. Matter of fact, we look at the MCV level to determine if it is a microcytic anemia or a macrocytic anemia, okay? Iron deficiency is a microcytic anemia. So the MCV on people who have iron deficiency should be below 80. Most of the time they're between 50 and 60. So they're little tiny red cells, okay? People that have megaloblastic anemia, which is known as vitamin B12 and folate deficiency or pernicious anemia, they tend to have larger cells. So their MCV is usually around 110, even up to 115 or 20, depending on the cells, okay? And we got a whole chapter on microcytic anemias and macrocytic anemias, okay? So don't go into panic mode. But I'm telling you they're important. This MCV is a very important indice on our CBC to look at, okay? Questions about MCV, guys? Yes, ma'am.
What does indices mean again?
Calculation, with the exception of the MCV. That's the only one. But it can be calculated manually, and it used to be calculated manually. Because a long time ago, where you notice it says on automated machines, it's actually measured, okay? But like in the old days, we did a spun hematocrit. We put the little stuff in the capillary tube, plugged it up, put it in a centrifuge, spun it down, and then we read it on a little machine, okay? And we're going to do that. We'll do that in the lab next week or so, okay? You guys are going to stick your own finger and do your spun hematocrit.
Do you guys use a chart?
No, we use a little reader. It looks like a chart, but it's like plastic. You know.
Yeah,
I'll
I
show
know
you.
what
Yeah, I'll show you. You probably used one if you were doing vet stuff. Okay. So back in the old days, you did a manual RBC count with a hemocytometer and a manual WBC count and a manual platelet count. Then you did a hemoglobin with a spectrophotometer, where you diluted, added the cyanide solution, killed all your red cells, and then read it in a machine. Okay. Then you did a spun hematocrit. So you had RBC count, platelet count, WBC count, hemoglobin concentration, and a hematocrit. You had all those information. So then you would take that information and then plug it into those formulas that we looked at a while ago. The hematocrit times the RBC count, or times 1,000 divided by the RBC count. Remember? A while ago? Okay? So you actually did calculate it in the past. Okay? But now the automated machines are doing the measurements too, with the exception of the MCV. MCV is measured, but MCH and MCHC that we're going to talk about in a minute, they're still calculated, okay, based off of the red cell count and the hemoglobin, okay? Does that make sense? That's the reason it's still classified as an indice, even though it is measured directly, all right? Questions? All right. So this kind of gives you a little chart for the same thing we talked about a while ago. All right, so here's the term anesiocytosis, if you want to go ahead and write this down, all right? Anesiocytosis corresponds to the RDW. And we talked about red cell width distribution a while ago on that little chart that had all the normal values, okay? When you have an increase in RDW, you have what's called anesiocytosis, okay? There's two terms that you're going to be familiar with, you're going to learn. There's one, anesiocytosis, and then there's going to be one called poikilocytosis, or poikilo, ever how you want to say it. I've always was taught it's poikilo. My Miss Wheeler that used to teach this class before me, she called it poikilocytosis. And I'll teach that one to you in just a minute also, okay? But here is anesiocytosis, so you know what it looks like when we're talking about it, okay? All right. MCH, mean cell hemoglobin. So this is the average amount of hemoglobin in the cells. In the lab, we don't really look at this that often. It comes across and we look at it, but it doesn't really tell us as much as the MCHC does, okay? So I tell you about the MCH, tell you what it is, tell you how to calculate it, and its normal value. But in the lab, we really don't look at it that often, okay? So just know what it is. It is the average volume or weight of hemoglobin, okay? Notice it's measured in picograms, okay? Picograms. All right. So, does not take account to the size of the cells. So there's the problem right there. So it's not a good accurate measurement. Even though it's there, we don't use it as much. So it must be interpreted along with the MCV. So we just don't really look at it that much as we go, okay? But MCHC, we do, Okay, so I'm going to introduce you to 3 more terms. Okay, so MCHC is known as the mean cell hemoglobin concentration. All right, it's the ratio of hemoglobin mass to the volume. All right, calculated using the hemoglobin divided by the hematocrit gives you your MCHC. 32 to 36 grams per deciliter. All right. So, MCHC, all right, normal is 32 to 36 grams per deciliter, okay? These are known as normochronic. Normochronic, all right? We want our red cells to be normocytic and normochromic. Okay? Now what that means is your red cell is like that, and it's got that little bit of central power right in the center. So that little white dot in the middle, like it's supposed to have. That makes sense? Okay? Alright? Anything that is less, so MCHC is less than 32 grams per deciliter, we refer to it as hypochromic. Alright? So how do I know a cell's hypochromic? So, if my cell's supposed to look like that, with a little central power, right? If I get this, and only this part's pink, then I have hypochromia. Okay? So in other words, I have a huge wide area of central power. That lets me know that I don't have enough hemoglobin in the cell to fill up the cell volume. Does that make sense? So I'm going to have that bigger wide area of my cell. So I don't have enough hemoglobin to stain, essentially. So you get a little pink ring around it. I think it's like 1/3, okay? 1/3 of the cell is central power. Okay? I'm going to say greater than 1/3. Okay? Greater than 1/3 of the cell is central power, in other words, the white, then I am hypochromic. Okay? All right, if my MCHC is greater than 36 grams per deciliter, then I am hyperchromic. Okay, now, listen to me very carefully. When I am hyperchromic, I have no central power at all. Okay? Here's the problem. Everybody looking at me, paying attention to me. This is very important. We never use the term hyperchromic. Okay? Here's why. Cells that don't have a central power are known as spherocytes. Okay? So instead of saying we have 1+, 2+, 3+ hyperchromia, we say we have 1+, 2+, 3+ spherocytes. Does that make sense? That makes sense? Okay? And so if they're missing that, it means instead of them being that biconcave disc, like what we think about cells being, red cells being, they're globes. They've been pushed out because they have so much hemoglobin that they're pushing the cell out compared to the size. Okay? So spherocytes are usually microcytes also. They're usually smaller and they're perfectly round and missing the central power. Okay? So instead of saying hyperchromic, we just say spherocytes present.
Does the spleen or the macrophages?
They try, yes. But there's actually a disorder, we'll talk about it later on. It's called genetic or hereditary spherocytosis. Somebody tell me y'all had somebody, you did, you told me you had somebody in your family that has,
My brother-in-law.
yeah, hereditary spherocytosis. So in other words, their cells are small, but their hemoglobin is large. They have a large amount of hemoglobin in the cell. And so instead of it being that cool biconcave disc, it pushes out, making it look like a globe because there's so much hemoglobin there. So you don't have that central power. So the terms we use most often are normochromic and hypochromic. Okay? Hyperchromic, if we have hyperchromia present, we just call it spherocytes because that's what they are. Okay? Does that make sense? All right. All right. All right, and that's exactly what these last two things are saying right there about the spherocyte and the 1/3, greater than 1/3 of the cell is hypochromic. And then the spherocyte's right there. Okay. All right, so those are the terms that we do use with the MCHC. And so this is something you should always comment on a morphology. Okay? All right. All right. RDWs. Let's talk about RDW a little bit. RDW, MCV represents an average of the RBCs, less reliable in describing the RBC population. So we use red cell distribution width, RDW. Okay? So this describes a variation in red cell size. All right? So if you're looking in your microscope, okay, so you're looking at your CBC to start with, and you see an RDW greater than 14, usually it's going to be around 15 or 16. Oops. 15 or 16%. When you look at your slide, you're going to see normal cells, you're going to see large cells, and you're going to see little cells. Okay? As you go, population-wise, you're going to see lots of different cell size variation. Okay? When you see that, this is known as a nisiocytosis. Okay? Increase in cell RDW means you have lots of different cell sizes, so it is known as a nisiocytosis. A nisiocytosis. Okay? There's actually a couple of things you can see nowadays. You can see RDW with a dash CV, which is coefficient variation. Y'all remember coefficient variation? What's coefficient variation? Y'all remember? Is it mean divided by the SD? Or is it the SD divided by the mean? Right off the top of my head, I can't remember. I think it's SD divided by the mean. Okay? Either way, so that's what we're looking at. We're looking at one standard deviation of the cells divided by the mean that you have, your X bar. And so that's what you have. And some machines actually are a little bit more technological. You'll see an RDW-CV, and you'll also see an RDW-SD. I'm talking about the actual standard deviation, okay? But RDW-CV is the one that is reported on most instruments, okay? Excuse me. All right. Yeah, by the mean of the MCV in this case, okay? So the SD of the MCV times 100 divided by the mean of the MCV. Okay. All right. So abnormal increase in RDW values. So this indicates heterogeneity or heterogeny of the RBC. So a difference in those cells. So when you use caution, of course, when interpreting the CV, you also need to look at the MCV too, and the population of cells. Okay. One thing that can give you a population of cells, and I don't know if you guys have ever, well, I know you hadn't because you don't know enough yet to think about this, but later on when you become a tech, and you're working in a hospital, you may see patients who have been transfused have high RDWs. Okay? Now, is that a true RDW or is that an artifact? It's an artifact. It's not their body having a high RDW. In other words, their body's not making a heterogeneity or homogeneity of cells. In other words, they may be making normal cells, but probably most likely they were probably making microcytes because they had anemia, had IDA or something else. And so then you transfuse them. Most people that donate blood have normal RBCs. And so what you do is you'll see a population of really, really tiny ones plus normal ones. And the normal ones are because of the transfusion that you've given the patient. Okay? We don't think about that a lot, but the older you get and the more seasoned tech you become, you'll see that kind of thing. All right? All right, so question about the indices. Okay? There's another index, it's called an MPV. It's a little bit later on, but we're not going to really talk about it, but it has to do with the size of the platelets. Okay? And it may actually be in here, but not yet. Okay? So reticulocytes. We've talked about reticulocytes already. We know what a reticulocyte is. Most of your analyzers do count retics now. Okay? They usually are immature cells still. They're missing the nucleus. They still have organelles, and they still have some RNA in them. So therefore, you know, they are still immature. Okay? So before they lose RNA and become a mature erythrocyte is what a reticulocyte actually is. They appear polychromatophilic, so they have that bluish tinge, and I showed you guys that on right stain the other day. This is what they look like. It's a little bit better. You can see the kind of bluish tint of them. Okay. Another thing you need to know about them is they're usually going to be macrocytes. You know, we talked about macrocytes a while ago. Their MCV is going to be a lot larger because they're more immature than a normal erythrocyte. Okay? All right, so look right here, guys. So this is a normal cell. Got a good central pallor. We can see it. Okay? This one would be still considered normal. It's a little bit, shape's a little bit unusual. But like this guy, look at this guy right here. See how dark it is and see how it's missing the central pallor? And look how perfectly round it is. This is a spherocyte. Okay? That cell is a spherocyte. All right? So if you see one like that, like that, like that, like that, these are spherocytes on this particular patient. Okay? And usually they'll stain a little darker red because they have so much hemoglobin in them. And the hemoglobin is what's actually taking up the stain. It's not the red cell itself, it's the hemoglobin inside it. Okay? All right? So reticulocyte count, what does it do? It indicates an effective bone marrow activity. Okay? So remember that 0.5 to 2.5% of your red cell count should be reticulocytes. Okay? It's one of the most useful and cost-effective lab tests in monitoring anemia. And we use a supervial stain new methylene blue, or just methylene blue. Okay? They use brilliant Crescel blue, but nobody uses that in the lab. Most of the labs use new methylene blue, so that's kind of what I teach you guys. That's what you will use in the lab. You actually going to do a reticulocyte count one day next week, probably. Okay? I might even do it this week. I haven't decided yet what we're going to do today or tomorrow. Okay? Method for counting reticulocytes, there are manual methods, which is what you guys will do in the lab. Automated methods, more precise. You know, you guys are going to count like 1,000 cells and do a calculation. The machine will count like, 40,000 cells or 50,000 cells. So, of course, it's always going to be more precise. The more cells you count, always the more precise it's going to be. Okay? So, reference interval, 0.2 to 2.5. I like 2.5, 0.5. I think 0.2 is a little bit low, but that's what the book gave you, so I wouldn't ever mark it wrong. But 0.5 to 2.5 is a better range for reticulocyte count. Okay? And this is what retics look like right there. That's a good picture. We've talked about them, looked at it, discussed them. This is actually stained with, this one is actually stained with brilliant crescent blue, but they look just the same with new methylene blue. So what you're looking for is these little blue dots in them, okay? You see those little blue speckles? Even in that one, even though it's only got 3 little ones there, you would still count that as a retic, okay? So what you would do is you would go through here and you would count the RBCs, that all of them. Every RBC, even if it is a reticulocyte, you still count it as an RBC. Then you would make a note on how many retics you counted in that field. Okay? So in this field, I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I would count 18 retics in that field. Okay? This one is blue, but I wouldn't count it as a retic because I'm not seeing any little blue strands in it. Does that make sense? Okay? So the key is the little blue dots. If you see the little blue dots, then you know that is RNA. Okay? And that's what we're looking for in reticulocytes. That makes sense? Okay. All right. Absolute reticulocyte count is the actual number. Okay? It is more effective or more diagnostic and informative to erythropoiesis than the percent. And so you should always look at that absolute retic count on your patients. Okay? All right. How do you calculate the retic? Well, most of your analyzers do it, but if you do the manual retic, then you can also do a calculation. It's the RBC count times 10 to the 12 per liter times your reticulocyte count percentage. And that should give you your absolute retic count. All right. Platelet count. Platelet count in MPV. Platelet count equals number of platelets per 10 to the 9th per liter. It is usually done in microliters also. So it's usually times 10 to the 3rd. So 1,000. Okay. Normal platelet count is between 150 to 450,000 is what most books look at. 150 to about 450 is what most places look at. MPV, mean platelet volume, it just represents the average volume. So if you had an increase in MPV, then you should see large platelets, what we call large platelets, okay, giant platelets. There's some disorders we'll talk about later on that have large platelets as a diagnostic thing, okay. Platelet count kind of does assess thrombopoiesis and also pathological conditions. You have patients come in with a normal a normal CBC, but their platelet count's off and like horrible, like 10, like 10,000 platelets, you know. Usually these are patients that are having liver disorders, okay. Your liver is a big place where platelets are stored, okay. Your spleen also is a place where platelets are stored. So any of those problems, spleen or liver, gives you a secondary decrease in your platelet count. Okay? All right? We'll stop right there. I'm tired. And you're tired. All right? So tomorrow in lab, we will probably look at like, I don't know what we'll do tomorrow. But we'll do something. I promise. Probably this week we will. We won't have a. I don't think we'll have a practical Thursday. This week we probably will just look at some more diffs. I'll tell you what I want y'all to do. I know what I want you to do. I want you to go back and redo your diffs tomorrow. Especially like those first 2 that you did. Go back and redo those and just kind of see if you do better, you know. And then we'll figure out something else to do. I might show you the hematology analyzers tomorrow also. Tomorrow and Thursday we'll look at the hematology analyzers. Okay? And then next week, though, we will get back into the nitty gritty. We'll do a reticulocyte count. Might let you draw your own blood. I'll teach you guys how to make blood smears. Show you how to use the stainer. We actually have a stainer here. So you can stain your blood and you do a diff on your own. And we'll let you run it through the machine and get your own CBC too.